All right, so in this video, I'm going to go through section 12.6, which is on cylinders and quadric surfaces for multivariable calculus. And the thing that I want to point out heading into this lesson is that in the last section in 12.5, we were really talking about equations of lines and planes. And so even though we were working in 3 dimensions, we were still dealing with with a plane, essentially a 2-dimensional surface. And now what we're going to start to get into is more the idea of 3-dimensional shapes. And as we go through this, there's going to be some vocabulary that you're familiar with, and especially this first part, that may be used in a little bit different way than you've seen before. So the first thing we're going to talk about here is what we call a cylinder. And you notice that I said cylindrical surfaces. So when we talk about a cylinder, and we're talking about 3-dimensional space, a cylinder doesn't necessarily have to be the traditional cylinder that you're accustomed to seeing. So like this one here, that's the cylinder that if I told you to draw a cylinder, everybody would probably think, okay, well, that's a cylinder. Well, look at the definition of what a cylinder actually is. Okay, so it says, let C be a curve in a plane and let L be a line not in a parallel plane. The set of all lines parallel to L and intersecting C is called a cylinder. C is called the generating curve of the cylinder, and the parallel lines are called rulings. So in this case, for the sort of traditional cylinder, we've got a circle, and that would be what we call our generating curve. Now, what's different here is we're looking at some different cylinders. So we have Z is equal to Y squared. So Z equals Y squared, if you just graphed that in the YZ plane, you would have a parabola. But in 3 dimensions, this becomes what we call a cylinder. So we've got this cylindrical surface that's got this parabolic shape to it. So you can see that in the ZY plane, it looks like a parabola, but now we're extending forever in the X direction. So that would be described as a cylinder. And notice that we have our generating curve, which is that parabola. And then all of the rulings are the lines that are sort of going out from that parabola that are creating this 3-dimensional surface. We also have another one here, Z is equal to sine X. So you know what the sine curve looks like. So essentially we're working in the XZ plane. And then now if we want to create that 3-dimensional surface, now we're going to expand that out in the Y direction. And that is a cylindrical surface as well. Okay, so when we are talking about equations of cylinders, it's a little bit different because we're used to seeing, a circle and then working off of that circle, and that's sort of how we figure everything out. But remember, that's not the only type of cylinder. So we can see equations like Z equals Y squared and Z equals sine X, and those are considered to be cylinders as well. Okay, so on this next problem, it says describe and sketch the cylinder given by the equation Y squared plus Z squared is equal to 4. And I already have this graphed on here, but I just wanted to show you that when you graph these things, make sure you're using sort of our traditional setup for your coordinate system. So Y squared plus Z squared would be a circle in the YZ plane with a radius of 2. And then from there, I'm just going to extend out forever in both directions. So typically, we don't necessarily show forever in both directions, but we show enough of the shape that you can get a feel for what it's going to look like. So in this case, it looks like I have a cylinder that has a specific altitude to it, but in reality, it's extending forever in both directions. Okay, so let's move on here and talk a little bit about another type of surface, which is referred to as a quadric surface. And this is much, much more complicated than dealing with a cylinder. When we talk about quadric surfaces, we have sort of a standard equation that we work off of. And there's a lot of different quadric surfaces. And what these are, in a lot of ways, are sort of 3-dimensional versions of our conic sections. And sometimes it's combinations of 3-dimensional, or I should say combinations of our conic sections. So here's our sort of standard equation. And if you think about when you work with conic sections in 2D, there's a standard equation similar to this. The difference now is we're adding in that Z coordinate. But notice that we have 6 different quadric surfaces. So we have what's called an ellipsoid, a hyperboloid of 1 sheet, a hyperboloid of 2 sheets, an elliptic cone, an elliptic paraboloid, and a hyperbolic paraboloid. So in terms of what these look like, if you look at the next page, these are the shapes that we're talking about. Ellipsoid is one that maybe you've seen before. The way that I would describe an ellipsoid is if you were to take a cross-section, the way that this ellipsoid is oriented in the three-dimensional space. If you were to take a cross-section in the YZ plane, you would see that you have an ellipse. If you were to take a cross-section in the XY plane, you would also see an ellipse. So that's essentially what an ellipsoid is. You can see that we've got ellipsoids really in every direction there. Or excuse me, ellipses in every direction. There's also one called an elliptic paraboloid, which is essentially a combination of a parabola and an ellipse. And when we start sketching these things, you'll kind of see where these names come from. We've got another one called a hyperbolic paraboloid. And so what we're looking at here is we've got a parabola in one direction, but if you look in the other direction, it sort of looks like a piece of a hyperbola. And that's what we're looking at with that one. So with a cone, when we talk about a cone in 3 dimensions, in 3-dimensional space, can extend forever in both directions. So we have an altitude line, and then we usually have sort of exterior lines that are going to form the outside of that cone, and those are going to extend forever in both directions. So if you were to take a cross-section of these cones, you're always going to see a circle. Like in this case, if I took a cross-section that went through the z-axis, perpendicular to the z-axis, then you would see circles. But those circles are going to extend forever along the z-axis, both up and down. Okay, and then we also have what's called a hyperboloid of one sheet. So on this one, when I take cross-sections, you can see that in one direction, I'm going to see a hyperbola. And then in another direction, it looks like we have a circle or an ellipse. And then we have what's called the hyperboloid of 2 sheets. And this one, you just think about with a hyperbola, we've typically, when we think of a hyperbola in 2 dimensions, we think of the 2 branches. So essentially what you're dealing with here are the 2 branches of the hyperbola, and that's what's creating that 3-dimensional shape. So you're going to have to know the names of these, and that's one of the hardest parts of this is really understanding what these look like. Really, the main purpose of what we're doing in this section is to introduce these figures, and we're not really going to do a lot with them. What we're going to do is understand what they are and how to identify them, because when we start getting into all of our vector calculus, and especially when we get into integration, we're going to see these figures showing up a lot, and we have to be able to identify them. We have to be able to do decent sketches of them as well. So what we're going to do on this first problem is we're going to go through and we're going to use traces to sketch this quadric surface. So we have x squared plus y squared over 9 plus z squared over 4 is equal to 1. So the first thing is I kind of want to know what shape I'm going to be sketching here. And we could figure this out when we start graphing it, but let's go over here and notice that in an ellipsoid, that's kind of the standard form of an ellipsoid, and that looks very much like what I've got here. So what we're going to do is we're going to create some 2D sketches to allow us to do our 3D sketch. And the way we're going to do that is we're going to use what we call traces. And traces are just basically ways that we can create sketches in our 3 coordinate planes, the XY, the XZ, and the YZ planes, and then we can sort of piece those together to create the 3-dimensional shape. So what I'm going to do here is I'm going to say, okay, for one of these sketches, let's let z equal to 0, and this whole thing then looks like x squared over 1 plus y squared over 9 is equal to 1. And you can see that's an equation of an ellipse. Okay, so what I can also do is I can say, let's let y equal to 0. Well, if y is equal to 0, then I have x squared plus z squared over 4 is equal to 1. And again, you can kind of see that this is going to be an ellipse now in the xz plane, and you can see where your major and minor axis is. And then the last one, we're going to let x equal to 0. And when I do that, that's going to simplify down to y squared over 9 plus z squared over 4 is equal to 1. And again, I can see that that's an ellipse. So by getting these traces, a lot of times we're able to figure out what the shape is going to be, because now I know that an ellipsoid is going to be a cross section of an ellipse in any direction, and I can see that that's what this is creating. Now, what you also do sometimes is you can create sort of general sketches. I can say, okay, so let's just say that z is equal to some constant value. If z is equal to some constant value, then in general, what we're going to see is x squared plus y squared over 9 is equal to 1 minus k squared over 4. And all I'm doing there is taking the equation that we had for the original ellipsoid, and I'm plugging k in for z, and then I'm solving into a standard form. Because remember, what's on the right side now would be a constant value. Okay, and we can do the same thing in any of the directions. So we could get x squared over 1 plus z squared over 4 equals 1 minus k squared over 9, and so on. So sometimes you're going to want those general equations, but typically when you're going to sketch these, this is what we're going to use, because those are the easiest ones for us to sketch in 3 dimensions. So now let's go through, how do we actually sketch this? Well, what I want to do is I want to create my coordinate plane here, or my space, my 3D space, and I know that the largest value I'm going to have in terms of the distance I have to go from the origin here is going to be 3 units, and that would go in the y direction. So remember, this is x, this is y, and this is z. And just like I've talked about before, now that we've gone through and we've talked about cross products, we know that I cross j is going to give me k. So I have to make sure I have the correct orientation for this when I set it up. But I'm actually going to mark out some values here just to make sure that I'm sort of scaling this consistently. Okay, so I can draw these ellipses in whatever direction that I want, but I'm gonna start with I'll go in the order that they're in. X squared over 1 plus y squared over 9 is equal to 1. So I'm in the xy plane. I know I would go 1 in the x direction, and I think what I'll do here is I'll make this a little bit different color. Go 1 in the x direction, and I'll go 3 in the y direction. Now, from what we know about conic sections, we know we're going to have another point out here, and we know we're going to go -3 units out here. And so essentially what we're going to get is an ellipse that looks sort of like this. Okay, so let me go back and redo that last section there. So we get an ellipse that looks kind of like that. Now that's in the XY plane. Now I want to do, and this will actually end up being on the front of my figure, so I'm going to go ahead and make that a solid line. Okay, so now I want to do the same thing with these other ones. Well, I have x squared plus z squared is equal to 4, and I also have x squared or y squared plus z squared, or excuse me, y squared over 9 plus z squared over 4 is equal to 1. So I'm going to do the second one, x squared plus z squared over 4 is equal to 1. So I know I need to go 1 in the x direction, and I need to go, in this case, I would need to go 2 in the z direction. And what you'll start to see with this is that this is going to start to fit together. So this is going to be kind of the front of my figure, and then it's going to go down here to -2, which we'll say is around there. And then this thing's going to loop back up. And when it loops back up, it's going to connect back up to where we started. So even with just 2 ellipses, I can already tell what this figure is going to look like. And I'm going to go ahead and connect it together now. So my last ellipse would go through here, and then I would have the bottom piece of it coming down through here. Okay, so there's my ellipsoid. Now, it's not the nicest looking thing in the world, and your sketches aren't going to be perfect unless you're very, very artistically inclined, which, like I've said before, I'm really not. But what I'm doing is, by showing this piece, I'm making it really clear what I'm doing, and it makes this graph make a little bit more sense. So I know that's a little bit messy. It's kind of hard to draw on the tablet with the stylus, but you get a feel for what I'm going for there. Okay, so what I want you to do is try this next one. It says classify and sketch the surface given by this equation, and notice that this one is not in the nice simplified form where it's easy to identify. So keeping in mind that we have those kind of standard forms above for each of the 6 shapes, Try to figure out which one that's going to fit and try to get it into the standard form that would fit that, and then go through the same process. Get a couple of traces that should allow you to then create your three-dimensional sketch. So pause the video, take a couple of minutes, do the best you can with the sketch, and then when you come back, I'll show you the solution. Okay, and here's what you should have ended up with on that one. You can see that the first thing I did was move the constant value to the right side, and then I divided everything by -12. And from that, it's a little bit easier to recognize that I am now looking at a, excuse me, a hyperboloid of 2 sheets. So for my traces, I just chose 2 things here. I said, okay, let's let z be 0. And that gave me -x² / 3 + y² / 4 is equal to 1. So that's going to be the graph of a hyperbola. And then when I set x equal to 0, I got y² / 4 minus z² / 1 is equal to 1. And that's going to give me a hyperbola as well. And you could see that if I were to set the y equal to 0, then I would have negatives there. It gets a little more complicated when you start dealing with that. So that's a little bit more chaotic in terms of trying to figure out the sketch. So you always want to choose what's going to make the most sense. And this is easy for me to get hyperbolas in those 2 directions. That's why I chose z and x the way that I did. Okay, so now you can see on my graph that what I tried to do was sketch out those hyperbolas. And once I had those hyperbolas sketched out, I could sort of piece together what the rest of this is going to look like. So it's a little bit complicated, but that's the idea behind it, is to use those traces and then connect the pieces together, knowing, you know, what these things are sort of going to look like in the end. If you have no clue what the thing's going to look like and you start sketching it, it makes it a little bit harder to do those 3D sketches. Okay, so we've got a couple more things here. The last thing that I want to do, and this is really a lot of practice for you, but the last thing I want to do is give you an opportunity to play around with these things a little bit. So I gave you a bunch of equations that are not in the easily recognizable forms for our quadric surfaces. And so what I want you to do is take these 6 equations, get them in sort of their, you know, standard form, and then in these equations, notice how there are A, B, and C values. What I want you to do is I want you to find the A, the B, and the C. And so you're going to identify what it is, get the equation in the right form, identify what it is, and then find A, B, and C. So I want you to pause the video, figure all those things out. Notice you don't need to graph this time, but figure all those things out, and then when you come back, I'll show you the solutions. Okay, so here's what you should have come up with on these. The ellipsoids are usually the easiest to identify because you can see we have a positive x squared, positive y squared, a positive z squared. The main thing is you need to have a 1 on the right-hand side. That one's pretty straightforward. The second one, you can see we've got a hyperbolic paraboloid. And the way that I can identify that it's a paraboloid is I can imagine how I would get a parabola in one direction, and I can also see how I would get a hyperbola in a different direction. So you have to sort of break this thing into the parts and think about, if I set one of the variables equal to 0, then what shape am I looking at in 2D? And in this one, I can see it's a combination of a hyperbola and a parabola. Okay, so that's really an easy way to figure out the name of it if you're not 100% sure once you've got the equation. Okay, so here's another one, 9x squared plus y squared minus 9z squared is equal to 9. So this is a hyperboloid of 1 sheet. A little bit harder on this one to identify it because you can see in one direction we are actually going to have an ellipse, and then in the other direction we're going to have a hyperbola, and then and actually 2 of the directions, I should say, we're going to have hyperbolas. So you can kind of see how that pieces together, but for the names of them, like for this one, because it's combined with the shape of an ellipse, that doesn't really show up in the name of it. So sometimes you just have to know based on the 2 hyperbolas and what the third part is, you kind of have to know how that's going to turn out. All right, and then the next one here, it's the hyperboloid of 2 sheets. You know, kind of the same thing over and over again. You just have to get used to these forms. Then we've got an elliptic paraboloid. And with the elliptic paraboloid, notice what the standard form is. We've got that z over 2 is equal to x squared over 4 plus y squared over 1. When you try to graph that one, you probably want to deal with the parabolas and not the ellipse, because notice on this one, if I were to set z equal to 0, well, I'm going to have x squared over 4 plus y squared over 1 is equal to 0, and that's not going to give me anything to graph. So I would have to choose a non-zero z, and then it becomes much, much more complicated to locate that two-dimensional shape in space. Okay, and then the last one's a cone. And for the cone, essentially what you're looking at there is, if I were to set any of those equal to 0, the x, the y, or the z, you can see how what you're going to get. And I guess I should say, if I were to set the x equal to 0 or the y equal to 0, you can see how I would get equations of lines. And then if I set the z equal to 0, you can see how now I'm starting to see what would appear to be a circle or an ellipse in the other direction. Okay, so that's a lot of what your assignment is. Really, the hardest part of this assignment is going to be doing those 3D sketches, and it just takes a lot of practice. And you have to, I guess, suffer is probably not the right word, but that's the word I'm going to use. You have to sort of suffer through it. You have to train your brain to do these things. And it's a little bit difficult at first. And again, if you're artistically inclined, this might come to you very fast. If you're not, like me, you might struggle with it a little bit, but do the best you can. And when you're done, if your shape doesn't remotely resemble the shape you know it should be, then I would just start your sketch over again. And the more times you do it, the better you're going to get with these.